Hello, everybody. Today, let's talk about lecture number 18, which is high performance concrete, number 4. So the last lecture on high performance concrete. So let me share the screen of my iPad with you. Okay, here we go. In this last lecture, number 18, we talk about, first of all, lightweight concrete, okay, and then we talk about polymer concrete, shotcrete. Okay. The first one is lightweight concrete, which is defined as a concrete with air dry unit weight less than 115 PCF. Okay, so for normal structural concrete, the density is around 150 PCF, or 2,400 kilogram per cubic meter of concrete. Okay, so less than 115 can be classified as lightweight concrete. Right. So depending on whether the sand and or the coarse aggregate, lightweight aggregate, we have the first one, all lightweight concrete, which means both the sand and the coarse are lightweight aggregate. If only the coarse aggregate are lightweight, we call that sand lightweight concrete. And for this type of concrete, it has higher strength because the sand is traditional normal sand, so the strength of the sand lightweight concrete is higher. So depending on the source of lightweight aggregate, for the sand, it has a bulk density less than 70 PCF. Okay. For coarse aggregate, the density is even lower. It's around 55 or less. Okay. Here show the picture of manufactured lightweight coarse and sand. As we can see, most of them are spherical shape. And depending on the source, we have natural lightweight aggregate, which is aggregate from natural rocks such as permites, scoria, and turf. Okay. Ancient Roman engineer used permites to make lightweight pozzolanic materials. Okay, so they ground the permites aggregate into powders and use these powders as pozzolanic materials to make the famous Pantheon. But more often, we use manufactured or synthetic lightweight aggregate, which is produced by such as expanded slag, sintered pulverized fly ash, or expanded clay. Okay, so this is manufactured lightweight aggregate. So compared to traditional concrete, lightweight concrete has this following advantage. The density is lower, okay, which translates into lower load onto the foundation and supporting structures. So we can have a smaller cross-section for the foundation, the beam, and the columns, and also we can reduce the material costs. And also, lightweight concrete is a high thermal insulator materials because these tiny air bubbles inside the aggregate is very good thermal insulator, and this air are not interconnected. So that will, reduce the cost for heating and cooling, and also make lightweight concrete more fire resistant. Okay. In the next couple of slides, let's compare the performance of lightweight aggregate with traditional concrete. Because the aggregate are lightweight, so when there's a segregation in the concrete, the aggregate will flow to the surface of the concrete. So this is the opposite as normal concrete. Because for normal concrete, the density of aggregate are higher compared to the density of cement paste. So when segregation happens, the aggregate will settle to the bottom of concrete. But lightweight aggregate are lighter, have a lower density compared to the cement paste. So when there's a segregation, the lightweight aggregate will flow to the top of the surface. Okay, so this is the big difference between lightweight concrete and normal concrete. The second one, the aggregate are very porous, and because of that, they will absorb a lot of mixing water. Okay, so remember when we design our concrete, the moisture condition of the aggregate should be SSD, okay, which means saturated surface dry. If lightweight aggregate is not in SSD condition, it will absorb a lot of aggregate, a lot of moisture from the cement paste. Okay, so that may change the water cement ratio in the cement paste quite a lot compared to what we design. Okay, so to compensate for that, we could do this. We could wet the aggregate before the mixing. Okay, so make the aggregate in at least saturated surface dry condition before we mix it with the other raw materials, the cement powder and water. Okay, so this is very good to reduce a potential autogeneous shrinkage, because for autogeneous shrinkage, the cement paste will absorb moisture from outside. Okay, but because the cement paste is so dense, curing is not very effective. So that's why for concrete has autogeneous shrinkage, if we use saturated lightweight aggregate, it will slowly release moisture to the surrounding cement paste, so effectively reduce the autogeneous shrinkage. Okay, but it is bad for freezing and soiling resistance, because when the lightweight aggregate is saturated with moisture and when the temperature below zero, it will become ice. So damage the aggregate and then crack the nearby cement paste. So it is bad for freeze and soiling resistance. Okay. The third point, aggregate has rougher external surface, especially for permites and other natural lightweight aggregate. So this makes lightweight concrete harder to pump. Okay, so we need to modify the mix design a little bit, such as increase the paste amount to compensate that. And the last one, compared to normal concrete, more cement paste is needed to achieve the same strength and workability. This is again because a lightweight aggregate is weaker compared to normal aggregate. For the concrete to have the same strength, we need to increase the strength of the cement paste, so that may compensate for the weaker aggregate. Okay. And also for workability, we need to increase the amount of cement paste to achieve the same slump, because lightweight aggregate is very porous, so that will reduce the workability of the concrete. Let's look at the mechanical properties. The strength is low compared to normal concrete if other mixed proportions does not change. Okay, so again, remember the strength of concrete is depending on the weakest link. Okay, because lightweight aggregate is weaker compared to normal aggregate, so we need to increase the strength of other component and reduce the amount of aggregate, lightweight aggregate, to increase the strength a little bit. Okay. For elastic modulars, it is also lower compared to normal concrete because the porous aggregate is softer, has lower E value compared to normal concrete. So as we can see, only 1/3 to 2/3 compared to the normal concrete. Okay. For shrinkage and creep of lightweight concrete are higher. Okay. Remember, when concrete shrink, only cement paste will shrink. Aggregate will act as restrainer. Okay. So if the aggregate is softer, the restraining effect will be lower. As a result, the shrinkage and creep will be higher compared to normal concrete. Okay. Finally, the failure mode. The failure will occur through the aggregate rather than around the aggregate. Okay, so this can also be explained using the weakest link series. We know for normal aggregate, for normal concrete, the weakest link is the ITZ or the paste. So as a result, the crack will try to go around the ITZ and the paste. Okay, not go through the aggregate. But for lightweight concrete, the weakest link is the aggregate. So the crack will try to find the weakest link, which is the aggregate. Okay. Okay, and then let's look at some other type of lightweight concrete. Ultra lightweight concrete is defined as a concrete with air dry unit weight less than 70 pcf. So very low. We know for the density of water is 62.4 pcf. So this is very close to the density of water. But the strength of this concrete is very low. Okay, so around 1 ksi. For structural concrete, we need 4 ksi or higher. So this is cannot be used as structural concrete. So mainly used for thermal insulation purpose. The last type of lightweight concrete is even lighter. So it's called aerated concrete or cellular concrete. This type of concrete has density lower than water. Okay, so 20 to 70 pcf, although the strength is very, very low, as we can see from here. Okay, so this is a picture of aerated concrete. There's actually no real aggregate in this type of concrete. The tiny air bubbles, which is generated by powders. Okay, this is one of the chemical equation. Aluminum powders with alkalis in the cement paste plus water, it will generate H2, which is hydrogen gas. And this will generate these tiny air bubbles in the concrete. Okay, and because we use the air as the aggregate, so the density is so low. All right, so that is short introduction of lightweight concrete. Next, let's look at a shotcrete. Okay, so shotcrete is a concrete which is pumped through the hose and nozzle onto a surface with very high velocity. Okay, no formwork is needed for this concrete as traditional concrete. We can use shotcrete as structure or non-structure component of buildings. Okay, again, we use compressed air to shot the concrete, mostly mortar, into a surface. The surface could be horizontal, vertical, or even overhead place. Okay. The coarse aggregate percentage is lower compared to traditional concrete, only around 20 to 30% coarse aggregate. And also the size is smaller because we need to shoot the concrete through the nozzle. Okay, if there's too much coarse aggregate, we're gonna lose these coarse aggregate particles when the concrete bounces off the wall. Okay, the velocity of the concrete we shoot that is very high, from 50 to 200 miles per hour. So if we use a lot of coarse aggregate, that will have a loss of the particle problem. Okay. So here shows the procedure when we apply the shotcrete. First of all, we need to clean the substrate. Okay, we use water and the high pressure to remove the dust and the sand of the substrate to ensure a good bonding between the shotcrete and also the existing structure. Secondly, the surface should be saturated into saturated surface dry condition to make sure the substrate will not absorb moisture from the shotcrete. Okay, at least overnight before the application of the concrete. Okay. After the shotcrete is applied, we should use wet curing. Okay, this concrete is easy to shrink a lot because the mix design is kind of special. So we need to use wet curing to reduce the shrinkage and ensure the strength development. Okay, at least 7 days. Shotcrete is brittle and may crack due to higher tensile stress. This is due to higher shrinkage value of shotcrete compared to normal concrete. Typically, the water cement ratio is lower. We use silica film in shotcrete, so that will increase the shrinkage of shotcrete. And also because we do not use a lot of coarse aggregate, potentially it will be oversanded, which means it has a lot of sand. So it may require higher amount of cement for good workability. The increased amount of cement will also translate into higher shrinkage. Okay, so as a result, shrinkage can be higher, up to twice that of normal concrete. Because the water cement ratio is low, we use silica film, so the strength will be higher. If the concrete does not crack, the durability will not be an issue, but we should pay attention to shrinkage cracking. The permeability will also be low because of low water cement ratio and also silica film. Other properties such as density will not be too much different from traditional concrete. Application of shotcrete, we can use the shotcrete in places where setting up formwork is not very easy. Okay, for example, tunnel and reservoir lining. Okay, we can also use shotcrete as protective coating for structural steel masonry on the rock. For structural steel, the building code specifies we need a certain type of fireproofing coating. So shotcrete is one of the options to fireproof the structure steel members. Okay. So that's the first part of lecture number 18. The second part, we're going to talk about polymer concrete.